Hello, this is Professor Gutierrez, and we are going to be looking at 5.2, or binomial probability distributions. These seem like they should be easy. You got two possible outcomes: success or failure. Now, depending on what you're studying, success may not be something you want. Success could be death from cancer, or it could be My Little Ponies, Bronathons. Ooh, weird stuff. But there are always two possible outcomes: success and failure. All right? And those are the binomial probability distributions. We have a fixed number of trials that we're looking at, so we're going to look at 1 trial or 2 trials or 100 trials, something like that. Each of the trials have to be independent so they don't affect each other. Each trial must have all outcomes classified into 2 categories: success and failure. Do or do not, there is no try. And the probability of success remains the same in all trials. Alright, so S and F, success and failure. Probability of success is P. P is equal to the probability of success. Remember that. Probability of failure is 1 minus P, or Q. Q is the probability of failure. N is the fixed number of trials. So I'm going to do it 100 times. So write the numbers down. P, probability of success. Q, which is equal to 1 minus P, probability of failure. And N, fixed number of trials. These numbers you will need to remember. X, a specific number of successes in n trials, so that X can be any whole number between 0 and n. So we could have 0 successful, we could have n successful. P is probability of success in one of the n trials. Q is the probability of failure in one of the n trials. And probability of X is probability of getting exactly X successes among n trials. Alright, so these are our variables we need to know. I've already told you about P, Q, and N. P, probability of success. Q, probability of failure. N, the number of trials. Now we're going to be introduced with X. X is a specific number of success in the n trials. P of X is a probability of getting exactly X successes among the n trials. You never succeed, you always succeed. You succeed 4 out of 17 times. Take a look. The word success is used arbitrarily, not necessarily good or bad. Alright, caution. All capital letters, so they're yelling at us. When using binomial probability distribution, always be sure that X and P are consistent in the sense that they are both referring to the same category, being called success. Example, Twitter. When is Twitter ever not a success? An adult is randomly selected with replacement. Doesn't really matter if you're doing it among the whole population of the US, say. There's a 0.85 probability that the person knows what Twitter is. I know what Twitter is. Based on a Pew Research Center survey. Suppose that we want to find probability that exactly 3 out of 5 randomly selected adults know what Twitter is. A, does the probability produce a binomial distribution? You betcha. B, if the procedure does result in a binomial distribution, identify N, X, P, and Q. Well, N, 5 randomly selected adults, so N equals 5. Exactly 3 of the 5 know what Twitter is, so success is if those 3 know. So, well, success is if they know. And we want 3 of them to know. X is equal to 3, N is equal to 5. P is a probability that one person knows, which is 0.85. Q is 1 minus 0.85, which is 0.15. Boom! They're doing it slowly. Alright, anyway, number of trials, 5. 5 trials independent because the probability of any adult knowing Twitter is not affected by it. And what do you consider an adult? What age? Like 18, 19, 20, 52, 5? I don't know. Each adult, 5 trials, outcomes. Each random such adult, 0.85. So we have our n, x, p, and q. N equals 5, x equals 3, p equals 0.5, q equals 0.13. We want x and p to refer to the same concept of success. They know what Twitter is. So we are good with that. 5% guideline for cumbersome calculations. When sampling without replacement, sample size is no more than 5% of the population. Treat the selection as being independent, even though they're actually dependent. Don't care. That's what I said earlier. It's so big that even if we don't replace, it's not going to make a difference, like taking a cup of water from the ocean. Is anyone going to miss it? No. Unless there's like a fish in it, then they might miss it. But they'll be missing the ocean. Like Nemo. Alright, so, oh crap. Alright, I'm going to leave it here for a sec. You will want to write this formula down. P of x equals n factorial, x minus n factorial, x factorial, times px, p to the x times q to the n minus x. For x equals 0 to n. N is the number of trials, x is successes among the n trials, p is probability of success, and q is 1 minus p, probability of failure. So this is the binomial probability formula. I'm going to write it down myself. Px equals n factorial, x minus n factorial, x factorial, p to the x, q to the n minus x, and there we go. Alright, so now we know all these numbers. We know the formula. We can plug it in for Twitter. So probability of 3 is equal to 5 factorial over 5 minus 3 factorial, 3 factorial, 0.85 to the third, 0.15 to the 5 minus 3. We plug that into our trusty calculator, and we get, I'm assuming, 1.38. What's the probability of getting 2? Well, we just plug in 2. Makes sense. 0. And remember, 0 factorial is defined as 1. So 0 factorial defined as 1. And you can actually define it as a continuous function. You get up into the higher mass, but we're not doing that here. Alright. That works. Using technology. Can we use technology to do the same thing? You betcha. We have a program called Excel. So we've already used it for a couple of things. We've used it for some graphs, we've used it for some other stuff. But we can use it for binomial distributions as well. Let's take a look. Alright, we're looking here. We're looking here. Got N, P, Q, that is Q, let's say that's X, this will be the probability of X. So, let's see. In our case, N is 5. P is 0.85. And Q is equal to 1 minus P. That's 0.15. That seems fair. So where was our formula? Our formula was, yeah. Nope, one more. Nope, one more. There we go. So X can equal 0. I'm going to figure out for each one of them. equal 1 plus enter. Copy, paste. One more. Just put 5 there. Don't have to do that. So this is equal to, so the probability of 0 is equal to n factorial. Well, now what is this? Is that combinations or permutations? That is combinations. So that is equal to combinations mine. So that's going to be n choose times p to the x times q to the n minus x. Now, that gives me something. Let's take a look at some stuff. What do I not want to change? So combine B1, A6. A6 I want to always change. So A6 is always going to be down. B1 is not going to go down. So that'll still always be in B, but that 1's not going to change. That 2 is not going to change. That 3 is not going to change. And that 1 is not going to change. There we go. So I should be able to copy and paste this all the way down to 5. Now, let's take a look here. Here, 0.138, probability of 3 is 0.138. Probability of 2 is only 0.024. So, see, there is a significant difference there. And probability of all 5 people knowing of Twitter is actually almost half. 0.44. Probability of none of them knowing it is very, very small. But now this will be my combination. What's graph look like? I'm going to do a little graph because I like graphs. Graphs are cool, aren't they? Don't answer that. Alright, looks like that. Kind of curvy, but you know. So that is interesting. Now, what if instead the probability were 0.5? How would that look? See, now I can just go up here and change this to 0.5, and then my graph's going to look like that. Oh, that's nice. That's also one of the advantages of putting the equations everywhere, is that it immediately changes everything. Over here, immediately. So, let's go back to here. Alright, boom. Using technology. I just showed you how to use technology. We don't need their stuff. Alright. Let's take a look at this one. As previously noted, between 1974 and 2011, there were 460 NFL games decided in overtime, and 252 of them were won by the team that won the overtime coin toss. Is the result of 252 wins in 460 games equivalent to random chance, or is 252 wins significantly high? We can answer this question by finding the probability of 252 wins or more. That is going to require some serious technology. We can do that. All right, coin toss is 50-50. So now what we're going to do is our number n, we have 460. That's the number n. And the result is 252 wins in 460 games, equivalent to random chance, or is 252 wins significantly high? We can answer this question by finding the probability of 252 wins or more in 456. So I'm going to start with 252. I'm going to copy this and paste it all the way down to 460. How about that? All right, so I am going to copy this. Put it here. Now, could always extend this to all 460. Let's see where the highest probability is, just for fun, Or at least see what it looks like. Interesting. I think it looks interesting anyway. All right, so what I want to do is find the total probabilities of 252 all the way to the top. So this is going to equal to the sum of this all the way to 460. So that gives us, if we add all those probabilities together, it gives us a 0.02245. Right. Right. PQ is 0.5, X from 252 to 460, and is equal to 460. Use technology. Boom. So 0.0224. So that is less than 5. This shows it is unlikely we would get 252 or more wins by chance. Therefore, we can reasonably assume that whoever wins the coin toss is more likely to win the game. And it's not just randomness. And then they do it their way because they're special. User Appendix Table 1A. I don't have a table. I don't have a table 1A. I don't have a book. They're both in the library. 2 books in the library, by the way. In case you did not know. Alright, another example. Based on a Harris poll conducted by someone I'm assuming called Harris, 60% of adults believe in the devil. I'm assuming that's in the United States. Assuming that we randomly select 5 adults from a church, use table A1 to find the probability. The probability of exactly 3 of 5 adults believing in the devil, and the probability that the number of adults who believe in the devil is at least 2. Alright, so they got some probabilities here. Like I said, I do not have the table there, so I would just plug it into my probability in Excel. And they add them all up and get 0.913. Now, what's interesting is they add 2, 3, 4, and 5. You could also take 1, subtract the probability of 0 and the probability of 1, which would probably be less work than doing all this. So consider that as another possibility. Right, a couple other things to remember. When you have binomial distributions, write this stuff down. This thing, the mu, the mean, is equal to n times q. Variance is npq. NPQ sounds cute. I think it is. Standard deviation is square root of that. And significantly low, less than or lower than 2 standard deviations below the mean. Significantly high, greater than 2 standard deviations above the mean. And that's going to be pretty common, 2 standard deviations above and below the mean. And when we start doing more z-score stuff, you'll see that. And then values not significant between those two. All right. P and Q had the 0.5 chance. Find the mean and standard deviation for the number of games, for the number of wins in a group of 460 games. Okay. Use the range rule of thumb to find the value separating the numbers of wins that are significantly lower or higher. Is the result 252 overtime wins in 460 games significantly high? So P is 0.5. 0.5, 0.5 times 60. Mean is going to be 230. Boom. About half of that. And then sigma is square root MPQ, which is 10.7. Random of 460 overtime games. Now, it is significantly high if it is above 2 standard deviations above. So 10.7 times 2 plus 260. Okay, we add those together, and we get 251.4. So 252 is just above that. So that means it would be considered significantly high. So it's just barely significantly high. It's not significantly high. See, funny jokes and statistics. They're pretty hard to come by. I don't know. All right, significantly high number of successes. This is what we get every time. If probability of X is more success than 0.05 or less, then this X is significantly high. Significantly low, less than 0.05%. All right, rationale for the binomial probability. Number of outcomes with exactly X successes, because we got combinations here. And the probability of X successes among N trials for any one particular P times Q. That works. And that is it for binomial distributions. Now, Poisson distributions are going to be pretty similar to binomial distributions, but we're going to be looking at extreme ends, basically. So that is something to keep in mind. And you'll see what I'm talking about in the next section. Bye for now. Poisson, oh wait, I gotta stop.